So in this module, I want to talk about sequential circuits. What defines a sequential circuits in digital systems is a circuit that have a memory component in it, like flip-flops and registers and the like, that store the state of the system at some point in time. So we're going to start by talking about regular sequential circuits. In the regular, because they exhibit some regular patterns, like registers or counters. For example, a counter increment by 1 or by a very specific number, so it has a very regular pattern. So we're going to call it a regular sequential circuits. We're going to start the module by talking about these and how we implement them using System Verilog, and towards the end we're going to talk about finite state machines, which are also sequential circuits, but they do not exhibit this regular pattern like the registers and counters and the other regular sequential circuits do. The output and state depends on inputs and previous states for finite state machines. It doesn't only depend on whatever comes before. Okay, so these are the distinctions. Okay, so I'll review the coding guidelines we've covered previously. So these guidelines, they are 4 guidelines, and the 2 in red are what's relevant to us now in terms of sequential circuits. So I will start by talking about the first one, the one on the very top, and which basically tells you that you should use always flip-flop or always FF and non-blocking assignments for registers. And later on, I'm going to talk about the last one, which is separate memory component for registers into individual code segments. Okay, so let's get started with that. So the way I'm going to explain the always FF and the first one is by talking about the most basic storage element, which is a D flip-flop. All of you should be familiar with what a D flip-flop is. It's the most basic storage element. Basically, whatever you put on its input, you will see on its output. So for example, if you put, let's assume that we have a D in here, and that's the input, you put a 1 in here, it will store that 1 internally, and it'll basically have that 1 on the output. And as you can see here, like this is the truth, or it's not a truth table because we're not dealing with combinational circuits anymore, but that's basically the functional table of this D flip-flop. For example, you can see that when the clock is 0 or 1, you're gonna just get whatever is in Q, that's basically the output you're gonna see on the output, or that's what you're gonna see on the output. However, on an active edge, and it just happened to be a positive edge, which is an edge that goes from 0 to 1 of the clock, you're gonna see that it will sample whatever is on its input D and just stores it. And that's how it is. And we're going to see some certain variations of it. For example, we might have a reset, we might have an enable here, and these you can actually review them. They're pretty simple. But what I want to do now is I want to show you how we actually implement these D flip-flops in Vivado, in the System Verilog, basically. So let's get to this. Okay, so we're going to see Vivado in here, and what I will be doing is I'll create a new source file, and that new source file, for example, I'm gonna create it and I'm gonna call it D underscore flip-flop, and of course it's gonna ask me for its inputs and outputs and whatnot, so I will rewrite them, or I'll write them separately. So let's do that. Okay, so we're gonna say yes, and then we're gonna see that source file here automatically because I deleted all the files in the project, so it doesn't have a top, so it automatically detected it and selected this one to be the top. Okay, so this is how it is. We start, and it's just a regular D flip-flop. Of course, like usual, so a D flip-flop should have inputs and outputs and whatnot. I'm just gonna take a look at it very quickly. So you can see here, I'm gonna start implementing the simplest of them here, and then I'll build to the more complicated ones. So in here, what I see is I have a D as an input, a clock as an input, and Q as an output. So that's what I should be capturing, okay? So let's do that. So what I have is here is an input, and it's type logic, and it's actually D. And I have another input, and it's also type logic, and it's actually the clock. And also I have an output, it's also type logic, and I'm gonna say call it Q, for example. And it's as simple as just following the rule. So what the rule tells me is, since I'm dealing with sequential circuit, what you have to do is you have to use always flip-flop. And of course, now it's not like the combinational. You should provide the sensitivity list, and generally speaking, you should provide a clock, whether you want to be on the negative edge or the positive edge. So I'm gonna just say the positive edge of the clock. That means I'm gonna activate this particular always statement or always block whenever the clock goes from 0 to 1, and that's end in here. And the code is as simple as saying, okay, the output should be equal to D, and I'm using non-blocking assignment because this is what the guideline is telling me. Use non-blocking assignment. And that's pretty much it. So this is how we implement a very simple D flip-flop. And if you go in here and you see the open elaborate design, for example, just to see what would Vivado interpret this code to be, you're going to see that it should interpret it as a D flip-flop. All right. So while this is working, I just want you to see that next we will be implementing the other D flip-flop. For example, when we're going to add a reset, and then we're going to add an enable, and we're going to see how that affect it. Okay, so as you can see in here, Vivado basically detected it as an RTR register because it's a single bit register. That's how it detected it. And it has a clock, it has a D, and it has a cube. That's exactly what I expected to see. So that's good. All right. So now we can actually modify this code a little bit and just add to it. For example, let's add the reset I talked about. Okay. So adding the reset is as simple as saying, okay, now I have another input, and that input I'm going to call it. It's also of type logic, and it's a reset. So I'm just going to basically put it here. And then the reset, there's a couple ways to use it. You have something what we call a synchronous reset and an asynchronous reset. So let's deal with the synchronous reset first. Synchronous meaning it only changes with the clock, which means that my sensitivity list here tells me that this always block, it will only be activated when the positive edge of the clock happens. That means this anything that happens will be with the positive edge of the clock if I don't add anything to the sensitivity list. So that will become a synchronous reset if I just do the following. If I say if it's reset, I want you to basically say Q is 0, okay? And that's basically a 32-bit 0, but it will be basically truncated to a single bit. So you can either say, well, I want it as a 1-bit 0 or 0. Vivado will figure it out, even though that 0 is a 0 decimal, which is 32-bit. And then else, what I need is I need the actual implementation that I have. And that implements a synchronous reset, because even if you click the reset, it will not change unless the positive edge of the clock happened, because this is the only time that would this is the only time that anything change in this D flip-flop. You can go through the schematic and see how it's happening, and it's like you're going to see that it's a synchronous reset. So if I want that reset to be asynchronous, that means I want it to reset and put that particular flip-flop to 0 anytime. You should add it to the sensitivity list in here. And we're going to say, for example, positive edge of reset, and this way you made that particular reset asynchronous, meaning it can happen even though the clock might be at 0, at 1, not at the specific edge. Okay, and that's how we do it asynchronous. All right, so what if I wanted to add something else? For example, an enable. Like sometimes we have not only a reset, but we also have an enable. For example, let me show you. This is the last one here. So what we have is we have the D, we have the Q, we have the enable, we have the reset. So the enable, generally speaking, is only basically if you put it to 1, the D flip-flop will operate like it's supposed to be. But if you put it to 0, it just stores the value and nothing happens elsewhere. So what we do is we basically just add another input, and that input we can call it enable, for example, or en. That's common, and you can see that it's as simple as saying else if enable, okay? And that basically makes it a synchronous enable. So it is enable, but it's synchronous. If you want it to change, which is not normal, you need to add it to the sensitivity list, okay? All right, so this is basically it. Okay, so this D flip-flop is just a single bit flip-flop. What if I wanted to make a register? A register is just as simple as basically telling me like, okay, the register is just basically 8 of these or 7 of these, depending on how many bits you want in that register. Let's assume that I want an 8-bit register. It's as simple as saying, okay, well, my input now, which is D, is going to be from 7 or from 0 to 7. Okay, and that makes my input an 8-bit input, which basically is a register, an 8-bit register. And I can keep the enable, I can keep the reset, I can keep the clock, and now my output has to be also from 7 to 0. And that's pretty much it. The rest can basically stay the same, nothing changed. Now I just made it an 8-bit register, even though this is called a flip-flop. You can change the module name. I'm just trying to save some time in here, but you can change the module name, and this made it basically an 8-bit register. And of course it does have a synchronous reset, or sorry, this is an asynchronous reset and synchronous enable. Okay, so it's an asynchronous reset, synchronous enable. Asynchronous reset, and it's generally, you should never use anything asynchronous in general sense. We usually do asynchronous reset because you just want to reset the system to an initial state, and that's the only case where you want to use it. Other than that, you should add another, for example, clear or something that is actually synchronous with a clock. But anyway, that's how easy it is. Let's assume that you want to make this 16 bits. Of course, you're going to have to go and add these 7s or modify them. But a better solution is actually to put them as a parameter. For example, you can say that I'm going to call this parameter n, and I'm going to keep its default value to 8. Okay, and then what you can do is substitute these 7, for example, by n minus 1, and the 7 by n minus 1, and now whenever you instantiate an instance of this particular register, which I'm calling the flip-flop, but it's a register, you can actually specify that parameter value, and you modify that particular register to an n-bit register. Whether you instantiate it with a 16 as the value of n or something like that, it's up to you. And that's basically how simple this is. So what I wanted to show you is the usage for the first guideline, okay? And I just showed it to you that you should always use always FF and non-blocking together when you're dealing with sequential circuits.